This lesson is about the addition and multiplication principles for counting. So first of all, we have this scenario. I have 5 different shirts, 6 pairs of pants, and 4 pairs of shoes to choose from when I get dressed in the morning. How many different outfits can I choose, assuming 1 shirt, 1 pair of pants, and 1 pair of shoes? And we're also assuming that we're not worried about fashion. For example, we don't care if I wear a polka dot shirt with striped pants. It doesn't matter, even though they don't match. Anyway, here we go. So first of all, we have 5 choices for the shirts. So I would start with 5. And then from each of those shirts, I could then have 6 pairs of pants to pick from, so times 6. And then once I've picked shirts and pants, I have now, from each of these possibilities, I have 4 pairs of shoes to pick from, times 4, and we end up with 120. And again, the key here was we picked shirts first, and then we picked pants, and then we picked shoes, and then we were done. So here's a similar scenario. The diagram below represents 4 towns, A, B, C, and D. Town A, town B, town C, town D, and different roads connecting them. So there's 3 roads connecting A to B, 4 roads from B to C, etc. How many paths are there from A to D, assuming, again, we're not going to backtrack and go again. So here from A to B, we would have 3 possible paths. And then once we get to B, no matter which of those paths we pick, we now have 4 possible paths to get from B to C. And then finally, when we're at C, we now have 2 more paths to pick to get to D. So we end up with 24 possible paths. And again, the reason we multiplied here was we made these choices, and then we were here, now we made these choices, and then we were here, and now we made these choices. And we didn't backtrack. Now this scenario is a little different. Again, I want how many paths are there from P to Q, but the problem is once I make that first choice, then I'm basically taking the north route, there's some possibilities, and then if I instead chose the south route, there's a different set of possibilities. So it doesn't quite work with the multiplication, although there is going to be multiplication involved. So let's start the north route. Well, if I pick the north route, there's only one way to do that first P to A, times, and then from A to B there's 2 possibilities, so times 2, and then from B to C there's 3 possibilities, so times 3, and then from C to Q there's 1 more possibility, so that's a total of 6. Now if I take the south route, well, from P to D there's only 1 possibility, and now there's 3 choices here from D to E, so times 3, and then there's 4 choices from E to F, so times 4. And then there's 2 choices from F to Q, so that times 2, which ends up being 24. Now the thing is that if I had chosen to go the north route, I could only pick here. If I had chosen to go the south route, I could only pick here. So it's not a choice and then another choice. I have to restart my counting from P again to figure out the south route compared to the north route. So in the end, I add 6 plus 24 to get 30 possible paths from P to Q. And I added because in order to do the second calculation, I had to restart my problem and calculate from there. So ultimately, the multiplication principle of counting says if you make one choice and then you make another choice, the number of possibilities is found by multiplying the number of choices available at each step. The addition principle of counting says if you have to restart in order to continue counting possibilities, then the number after the restart is added to the number before. So it's all about whether it's one choice and then another choice and you're continuing that process on, or you have to start over again, restart your counting, in which case then you add. So an ice cream shop has 7 flavors of ice cream to choose from. You can choose a single scoop, a double scoop, or a triple scoop with any combination of flavors you want. If you include the order of the scoops, which one's at the bottom, which one's at the top, etc. So for example, vanilla on bottom, chocolate on top is different from chocolate on bottom, vanilla on top. Then how many different cone selections are possible? Well, first of all, I could choose a single scoop, and if I picked a single scoop, I would have exactly 7 possibilities. But now I have to restart and say, well, what if I did a double scoop instead? So I do plus. Now for a double scoop, I have 7 choices for the one that's on the bottom. And there's no restrictions here. It didn't say you couldn't have a double chocolate, so I would have another 7 choices for the one on the top. So 7 times 7 because I make a choice for the bottom and then I make a choice for the top. Now I got to restart again and say, what if I decided to do triple scoop instead? So plus again. And now, well, for the bottom scoop, I would have 7 choices. Times for the middle scoop, I would have 7 choices. Times for the top scoop, I would have 7 choices. And that ultimately will be our answer. And we end up with 399 possibilities. So once again, single scoop, restart, double scoop, multiplication, because it's one choice after the other, restart, triple scoop, multiplication again, one choice, and then another, and that's how we end up with our answer. Okay, there are 6 books on my shelf. How many ways can I arrange the 6 books in a row? Well, first of all, for the very first book, I have 6 possibilities. Now I'm continuing my choices. So I made the choice for the first book times, but now I only have 5 books left to choose from because the first book's already on the shelf. So times 5 possibilities. And now I'm continuing, and then I make another choice. So now I've only got 4 books to choose from, so times 4. And then I make another choice, times 3. And then I choose times 2. And then finally there's only one left, so I choose that one, times 1. And this gives me 720. Now this is an example of what is called a factorial. So we say 6, and then we use exclamation point. 6 factorial is just 6 times 5 times 4 times 3 times 2 times 1. And then, for example, 8 factorial would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, etc. So a factorial, and there's a button on the calculator I'll show you in a second, basically you take the number that you have and you start multiplying down until you get to 1. So it has to be a positive integer, although I'll talk about 0 factorial in a little bit. Okay, so now let me show you how to plug it into the calculator. So first, on a blank screen, you hit the button 6. Then you hit the math button. Then you scroll over to probability, P-R-O-B. Then you scroll down to 4, which is the exclamation point or factorial. Then you hit enter. And now the screen should look like this. And you hit enter one more time and it calculates it for you and you get 720. So again, you have to type the number first, then go to math, over to probability, find the factorial button, hit enter, and then hit enter one more time to do the calculation. If you don't do the number first, it'll take whatever the previous answer was that you had and do it factorial on that number. So be aware of that. So now let's think about 0 factorial. So if you think about what we did over here, we had 6 books and we arranged them in a row and we got 6 factorial different arrangements. Well, the factorial does exactly that. It takes how many of our objects you have and it arranges them in a row. Well, if you have 0 objects and you want to arrange those 0 objects in a row, there's exactly one way to do it, to leave the space blank. So 0 factorial is exactly 1. So that's a useful thing to know. You can check it on the calculator if you want, but 0 factorial is equal to 1. And that's just something you just need to know. There, again, I gave the explanation for it, but it comes in handy quite a bit moving forward. And as long as n is a positive integer, then n factorial is n times n minus 1 times n minus 2 all the way down to 1. Okay, so let's do a couple more examples like this. So how many different quote-unquote words can I make using the letters of peanut? Well, there are 6 letters. So I have 6 choices for the first letter, and then 5 choices for the second letter, and then 4 choices for the third letter, and then 3 choices for the fourth, 2 choices, and then 1 choice. And again, I make a choice, and then I make another, and then I make another. Or in other words, you can call this 6 factorial. And we did this calculation on the previous page, which was 720. Now for problem 8, how many different quote-unquote words can I make using exactly 3 of the letters of peanut? Well, I have 6 choices for the first letter, and then 5 choices for the second letter, and then 4 choices for the third letter, and then I stop. And when I calculate that, I end up with 120 possibilities. So now I want to see how many words, quote-unquote, I can make using the letters of Canada. Now the thing here is that there's 3 A's and they're indistinguishable from each other. So when I rearrange the letters and make a word, the A's are interchangeable and I don't know the difference. So one possible quote-unquote word would be NACDAA. But I'm now going to color code these words with different colored A's so I can tell them apart. So this is one possible NACDAA, but this is another one where I just switched these 2. It's still the same 6 letters in the same order, but the choice of which A went where is different. And now this is the entire list of rearranging all the different A's in their colors, whether the red A is first and then the blue and the green, or the blue A and then the red and the green, etc. So these are the 6 possibilities, and all 6 of those represent this one single word. Now there are exactly 3 factorial ways that I could have made these rearrangements of the letter A, because I have 3 choices for what color goes as the first A, 2 choices for what color goes in the second A, and then 1 choice for what color goes in the third A. So there are 3 factorial different ways of arranging the A's within a particular word. So that means that I've overcounted by a multiple of 3 factorial, by a factor of 3 factorial. So to calculate the actual number of words using the letters of Canada, I would first have 6 factorial because there are 6 letters, and then I know that I've overcounted, so there's 3 factorial overcounting calculations being done. So 6 factorial for all the letters divided by the 3 factorial because of the repeat A's, and when I simplify that, I get 120. So once again, I want to find the number of quote-unquote words I can make using the letters of Mississippi. So there turn out to be 11 total letters. So I would have 11 factorial on the top. And then I have to divide out by any overcounting or multiple countings. Well, there are 4 i's, so rearranging the i's should be indistinguishable. So 4 factorial has to be canceled out. And then there are 4 s's, so I also have to cancel out 4 factorial for the s's. And then there's 2 p's, so I have to cancel out 2 factorial for the p's. And now I can plug this very carefully into my calculator using parentheses. So it should look like this on your calculator: 11 factorial divided by parentheses 4 factorial times 4 factorial times 2 factorial. That way the order of operations are preserved, and we end up with 34,650. So again, the repeat letters had to get canceled out on the factorials in the denominator. So now let's talk about just working with factorials, doing some simplification. So for 11 factorial over 8 factorial, I'm going to think of it as 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Well, I now notice that the 8's canceled, and the 7's canceled, and the 6's canceled, and the 5's canceled, and the 4's canceled, and the 3's canceled, and the 2's canceled, and 1's canceled. They don't really have to. So it's really 11 times 10 times 9. But a better way to write that would have been 11 times 10 times 9 times, and then 8 factorial over the 8 factorial from the denominator, and just cancel out 8 factorial instead. And so that's just 11 times 10 times 9, which ends up being 990. So here's another one. I got 7 factorial over 4 factorial, 2 factorial, 0 factorial. So first of all, I'm going to write it as 7 times 6 times 5, and then times 4 factorial. Divided by the 4 factorial times the 2 factorial times the 0 factorial. And the reason I stopped at 4 factorial is because 4 factorial is the biggest one on the bottom, so I want to cancel as much as possible. So that will now cancel the 4 factorial here, we'll cancel the 4 factorial here. And so what we're left with now is 7 times 6 times 5 over, well, 2 factorial is 2 times 1, and then 0 factorial is just 1. And so now I can simplify this, and we end up with 105. Now in this one, I've got 2 terms in the numerator, so I'm actually going to factor from those 2 terms. And I notice that 7 factorial is really 7 times 6 factorial, so these 2 terms have 6 factorial in common. And then what's left over is the 7 from the first factorial, and then minus, when you take everything out of something, it's minus 1 left over. If you want to think about it, it's like a 0 factorial left over, which is 1. And that's now still being divided by 6. But wait a minute, 7 minus 1 is just 6. So 6 factorial times 6 divided by 6, I can cancel these 6's, and we're then left with 6 factorial, which if you want to calculate what that is, it's 720. So now we're working backwards. We want to write these using factorials. So what's going on here? We have 9 times 8 times 7. And then if I wanted to keep that factorial going, I would have a 6 factorial left over. But I have to cancel out with a 6 factorial. That's basically multiply by 1. Multiply the 6 factorial on the top, 6 factorial on the bottom. And so I end up with this. These are uncanceled now. So the top is really just 9 factorial. And the bottom is 6 factorial. Same thing with the next one. Really, it's 12 times 11 times 10 times 9. And then let me copy the bottom, 4 times 3 times 2 times 1. And then to complete the factorial on the top, I need an 8 factorial because it's all the way down to, already got to 9. So I'm going to multiply by 8 factorial on the top and also 8 factorial on the bottom. And so really the numerator now is 12 factorial. The denominator is now 4 factorial times 8 factorial. All right, so here we are asked to factor and simplify. Well, first of all, between these two terms, the 8 factorial and the 6 factorial, they both have at least 6 factorial. So factor out 6 factorial. And then what's left is, well, there's 8 times 7 from the first one, and then plus 1 from the second one. And then 8 times 7 is 56, and 56 plus 1 is 57, so 6 factorial times 57. It says leave the answer with factorials, so I'm going to leave the 6 factorial alone. I'm not going to try to figure out 57 with factorials. Now here's the last one. I've got 3 terms here. The most that I can take out in common is 8 factorial. They all have at least 8 factorial. So I'm going to factor out 8 factorial. That's going to leave me with 10 times 9 from the first one, and then minus 9 from the second one, and then plus 1 from the third one. And when I do 10 times 9 is 90. 90 minus 9 is 81, plus 1 is 82. So this is 8 factorial times 82. And again, I'm going to leave it that way with the factorials in it. And that's the end of the lesson.